Welcome back to HansonMath.com videos. Today's lesson revolves around the inverse of a square matrix and how to find it. But before we get into that, I'd like to talk a little bit about what is an inverse to begin with. So this goes back to really the middle school years when you talk about what is the definition of the multiplicative identity property. If you remember, it simply means that anytime you multiply a number by 1, the result is the original number. In other words, multiplying by 1 preserves the original number's identity. For example, 23 times 1 is still equal to 23. See, the number 23 gets to keep its identity. With matrices, the idea is very similar. However, instead of multiplying a matrix by a scalar of 1, you can multiply by what's called the identity matrix. The identity matrix is a square matrix consisting of 1s on the diagonal and 0s elsewhere, such as right here in example 1. This is the identity matrix with 1s on the main diagonal and 0s elsewhere. So what we'll do is the following. We'll take matrix A, which I arbitrarily picked values for the 4 elements of this 2 by 2 matrix, 1, 2, 3, 4. And we're going to multiply by what's called the identity matrix 1, 0, 0, 1. And we're going to find out what is matrix A times the identity. Let's see what happens. So when we have a 2 by 2 matrix multiplied by another 2 by 2 matrix, the result is also a 2 by 2. So let's set that up. We're going to have row 1, row 2, column 1, and column 2. So first we're going to have the elements of row 1 times the elements of column 1. 1 times 1 is 1, plus 2 times 0 is 0. Okay, now we'll stick with row 1, and we're going to move on to column 2. So we've got row 1 times column 2. First element times first element, 1 times 0 is 0, plus 2 times 1 is 2. Okay, row 1 is all set. So now we're going to work on row 2 business. We have row 2 times column 1. 3 times 1 is 3, plus 4 times 0 is 0. And then finally, we're going to do row 2 times column 2, which will give us 3 times 0 is 0, plus 4 times 1 is 4. Notice all the zeros we have not adding to the identity of the original numbers, and we're left with a matrix of 1, 2, 3, 4, just like we began with. So this is a little example of how when you multiply any matrix by its identity, you truly do get back to the original matrix. Next, we're going to talk about the multiplicative inverse. If you remember, the multiplicative inverse is the number you multiply to another number to get 1. For example, 8 times what would equal 1? Well, it's the reciprocal of 8, also known as its multiplicative inverse, which would be 1/8. With matrices, this idea is very similar. If you multiply matrix A by its inverse, you're going to get what's called the identity matrix, as we've seen above. Okay, so let's try example 2. This is another matrix multiplication. Let's see what happens if we multiply matrix A times matrix B. Again, we have a 2 by 2 times another 2 by 2, which will result in the product 2 by 2 matrix. So we're going to have row 1, row 2, column 1, column 2. And now let's multiply row 1 by column 1, and we'll start to get our product matrix. -1 times 1 is -1, plus 2 times 1 is 2. Okay, now we'll do row 1 times column 2. -1 times -2 is 2, plus 2 times -1 is -2. Okay, we're all done with row 1. So now we'll move on to row 2. So row 2 times column 1. -1 times 1 is -1, plus 1 times 1 is 1. And finally, we're going to multiply row 2 times column 2, which would give us -1 times -2 is +2, plus 1 times -1 is -1. Summing up the entries at every element position, we get -1 plus 2 is 1, 2 plus -2, 0, -1 plus 1, 0, 2 plus -1, 1. Wow, look what we got here. We've got ourselves a 2 by 2 identity matrix because we have we have ones on the diagonal and zeros elsewhere. So look what happened. We multiplied matrix A times matrix B and we got the identity. So what must be true of matrix A and matrix B? They're inverses of each other, which is why we got the identity. Okay? That begs the question though, how do we find the inverse in the first place? How did I know that B, for example, is the inverse of A and we'd multiply to get the identity? Well, here's some fine print. If a matrix A has an inverse, matrix A is called invertible or non-singular. Otherwise, matrix A is called singular. A non-square matrix cannot have an inverse. Only square matrices have an inverse. And even then, not all square matrices have an inverse. But if a matrix does have an inverse, that inverse is unique, meaning there is only one. Next, we're going to look at ways in which you can find the inverse of a matrix. In this example, we're going to look at finding the inverse of this 2 by 2 matrix right here. And we are going to look at a way that really kind of reiterates the message of what an inverse is and what it does. So what I'd like to do is I would like to recopy this matrix, which has elements 1, 4, -1, and -3. And for simplicity, we'll call it matrix A. I know that there exists some matrix that I can multiply by that is the inverse of this, called matrix A inverse, such that I must get the identity matrix, which of a 2 by 2 is 1, 0, 0, 1. Okay, so since this inverse of A is currently unknown, I'll represent it with the variable x at each element. This element is unknown, but its position is row 1, column 1, which going forward, I'll just call it x11. This element is unknown, and it's in row 1, column 2, unknown in row 2, column 1, and unknown in row 2, column 2. So now this gives me a way to move forward. I can multiply using matrix multiplication rules, matrix A times A inverse. And we'll do that right now. If we do row 1 times column 1 and put it in the form of a new matrix, still going to be equal to the identity, we will get the following. We'll get 1 times x11 is x11, plus 4 times x21 is 4x21. Okay? So next element, now we're going to do row 1 times column 2. 1 times x12 is x12, plus 4 times x22 is 4x22. Okay? Now we will move on to row 2. So now we're here at row 2 in purple, and we're going to multiply that by column 1. Negative 1 times x11 is negative x11. Negative 3 times x21 is a minus 3x21. Moving on to the last element here, which would be row 2 times column 2, we have negative 1 times x12, which is a negative x12, and we have a negative 3 times x22 or x22, which is a negative 3x row 2 column 2. Now, what this is going to allow us to do is it's going to allow us to have really a system of equations where I can set up the column 1 here and rewrite it. So I've got x11 plus 4x21, and that has to equal the matching element over here, because this element here in row 1 column 1 has to be equal to this. So this is equal to 1. And then I also have negative x11 minus 3x21, and that has to be equal to 0 because that's its matching element. Okay? Now, on column 2, I have x, I've got to get back to my pen. I've got x12 plus 4x22, that's coming from here. And underneath that, I have negative x12 minus 3x22, and respectively, this position equals 0, and this position equals 1. Okay, so now what I have here is I've set up for ourselves a nice systems of equations, and we're going to be able to find out what these unknown x variables are worth. So with this system right here, we're going to sum it up and see what happens. x11 minus x11 cancels. 4x21 minus 3x21 is x21, and 1 plus 0 is 1. So now we have a known quantity, which I'll get to in just a minute. On the other system from the other column, we have x12 minus x12 cancels. 4 minus 3 is 1x, row 2 column 2, and 0 plus 1 is 1. So these are literally element values in our new matrix, where we have x in row 2 column 1 is worth 1, and x in row 2 column 2 is worth 1. Now how can we find this element of row 1 column 1 and this element of row 1 column 2? Well, substitution is the answer, because we know that we know the value of these equations. So since we know x21 is worth 1, I can plug that in right here. 4 times 1 is 1. Subtract that to both sides. 1 minus 4 is negative 3. So now I know x11 is negative 3. And likewise, in this equation, since we know that x22 is worth 1, I can plug that in right here. 4 times 1 is 4. Subtract 4 to both sides. 0 minus 4 is negative 4, which is x12, which goes right here. So we have found through algebra that the value of the inverse of matrix A is worth this 2 by 2 matrix with the following elements. As we continue on, we're going to look at the same 2 by 2 matrix, 1, 4, negative 1, negative 3, and we're going to look at an alternative way to find its inverse. This involves essentially creating a double matrix of sorts, where you have this 1, 4, -1, -3 matrix, and you augment that with the identity, which is 1, 0, 0, 1. So if you do that, now we've created a 2 by 4 matrix. The goal of this would be to use Gauss-Jordan elimination to get this here into reduced row form. For the purposes of this video, I'd invite you to hit pause and use a graphing utility on your calculator. Enter this 2 by 4 matrix into, say, matrix A, and then perform RREF, reduced row echelon form of matrix A. If you do that, you should get the following. You should get another 2 by 4 matrix that looks like 1, 0, -3, -4, 0, 1, 1, 1. Now, if you're paying close attention, this should look very similar because this is the identity, this is the solution, this is the inverse matrix, which is the same thing we got in the previous example. This is just an alternate method if you wish, and again, you can do it by hand using basically Gaussian elimination, Gauss-Jordan, to do a reduced row echelon form, and you get this, and the right side is your inverse matrix, -3, -4, 1, 1. Moving on, examples 5 and 6, they regard just straight up using a graphing utility to find the inverse. So if you take your graphing calculator and you enter matrix A here as a 3 by 3, and you put it all in correctly, and you go to, on most calculators, like on a TI-84, it's second matrix, brings up the menu, and you select matrix A if you entered it that way. And then you hit the inverse button, which on your calculator looks like x raised to the power of -1. That's the inverse. If you do that and it works out correctly, you should get the following: -2, -3, 1, -3, -3, 1, and -2, -4, 1. This is a way to find an inverse, not by hand, but by using technology. In example 6, we have a situation where if you enter this into your graphing utility, which I'd invite you to perhaps pause and give it a try. If you enter matrix A or matrix B or whatever you want to call it into a 3 by 3 and take the matrix and apply the inverse, it's going to tell you error, singular matrix. That means there is no inverse. Recall that we talked about at the start, not every matrix has an inverse. In fact, to even have the capacity to have an inverse, you have to have a square matrix, but even amongst square matrices, some have no inverse. Next, we're going to move on to a special formula that works only on finding the inverse of a 2 by 2 matrix. And I would say, in my experience, most high school students really prefer this method. It's a formula where if you refer to the 4 elements of the 2 by 2 matrix as A, B, C, and D, the inverse is equal to 1 over the product of AD minus BC times the elements rearranged as D, the opposite of B, the opposite of C, and A. So moving right along, and feel free to hit pause at any time. If this is element A, this is element B, this is element C, and this is element D, we're going to try to use the formula for the inverse, which says that we have 1 over AD is this diagonal product kind of with a negative slope. 3 times 2 is 6, minus the product of BC, which is kind of the positive sloping diagonal. Negative 2 times negative 1 is positive 2. And we multiply that by the elements. D now goes in the upper left, or row 1, column 1. So that is 2. This spot here is the opposite of B. So instead of negative 1, it's positive 1. This spot here in row 2, column 1 is the opposite of C, which would be positive 2. And in this lower right corner, row 2, column 2, we have A, which was 3. All right, now all there is to do is simplify. We've got 1 over 6 minus 2 is 4. We have that multiplied by 2, 1, 2, 3. Now we're going to use the distributive property, essentially multiplying through the scalar. 1/4 of 2 is 1/2. 1/4 times 1 is 1/4. 1/4 times 2 is 1/2 again, and 1/4 times 3 is 3/4. So there is your inverse of this 2 by 2 using this special formula, which most students really prefer. But again, it's only useful for a 2 by 2 matrix. In our final example today on this hansonmath.com video, we'll look at a particular application of the inverse matrix to solve a system. Now, you might feel that you're already prepared enough. You know how to solve this using elimination, putting it into a reduced row form, things of that nature, using RREF on the calculator. There's lots of options. This is just an alternative. So what you can do is as follows. You can create a coefficient matrix of the left side of the equation, which I'm going to call matrix A, and that is the coefficients of X, Y, and Z for all 3 rows, which would be 2, 3, 1, 3, 3, 1, and 2, 4, 1. Okay? Now, if you multiply that by what I'll call the solutions matrix, which is X, Y, Z, if you literally do the math and multiply this 3 by 3 times this 3 by 1, you will get right back to this with the variables included. Okay? So that gives you this entire left side of the system, and that has to equal the right side of the system, which I'll call B, which is -1, 1, and -2, which is coming from here. Okay, so mathematically this is sound, but boy oh boy, if we could just find a way to get this by itself, we can using the inverse. If we take the inverse of A and multiply that to both sides, symbolically that would look like the inverse of A times this solution matrix equals the inverse of A, because whatever you multiply on one side, you have to do to the other, times B. So what happens next is the inverse times the matrix A cancels to 1. So you have the solution matrix is equal to A inverse times B. So this might be a good time to hit pause. If you enter this into your graphing utility as matrix A and enter this as matrix B, and if you perform A inverse times B, you will get the following matrix of 2, -1, -2. So that is the solution to the system. X is worth 2, Y is worth -1, and Z is worth -2. So many would prefer to stick to RREF, but this is an alternative using the inverse matrix. Thank you very much. Feel free to rewind and watch certain parts again. And have a great day. And I look forward to your next viewing of my YouTube videos from Hanson Math.